All right, let's do one final example of sketching a graph of a rational function. Here we have the function f of x is equal to 3x to the fifth power plus 2x divided by x squared minus x. Again, this is a rational function because we have a polynomial divided by a polynomial. So, step number one, we want to factor the numerator and the denominator. Whenever you guys go to factor polynomials, the very first thing you want to do is factor out a greatest common factor. Notice that the numerator and the denominator both have a common factor of x. My numerator factors into x times the quantity 3x to the fourth plus 2, and my denominator factors into x times the quantity x minus 1. This will allow us to find our domain. What makes this function undefined? Well, to do that, we find the zeros of the denominator. Notice that the denominator equals 0 if x is 0 or if x is 1. This means that the domain of the function is all real numbers except for 0 and 1. Now, again, recall that wherever your function is undefined, you have the possibility of either having a vertical asymptote or a hole. Start by finding the vertical asymptotes. And to find the vertical asymptotes, begin by crossing out any common factors. Notice that we have a common factor of x and x in between the numerator and the denominator. If I cover up those common factors, the remaining factor is x minus 1. That tells me that x equals 1 is going to be my vertical asymptote. Okay, x equals 1 is the vertical asymptote of this function. So what about holes? Well, holes occur at any of the remaining undefined values. We said that this function was also undefined when x equals 0. Notice we have the common factor of x and x between the numerator and the denominator. Therefore, we have a hole when x is equal to 0. Now, if we want to find the coordinates, x comma y, of that hole, we want to plug in 0 into the form of our function where we have canceled out common factors. So notice if I cancel out this x and then plug in 0, 3 times 0 plus 2 gives me 2. 0 minus 1 gives me negative 1. When I plug in 0, I get out 2 over negative 1, which is negative 2. 0 comma negative 2 is the coordinates, the ordered pair of our hole in our graph. After we determine vertical asymptotes and holes, we want to look at horizontal asymptotes. Where does this function have a horizontal asymptote? Well, to do that, we must analyze the degree of the numerator and the degree of the denominator. In this case, we see that the degree of the numerator is 5 and the degree of the denominator is 2. If the degree of the numerator is greater than the degree of the denominator, we do not have a horizontal asymptote. All right, horizontal asymptotes are not applicable. Next, let's find our x-intercepts. To find x-intercepts, we need to look at the zeros of the numerator. Well, the zeros of the numerator are x equals 0, and that can't be an x-intercept because it's not in the domain. Notice that plugging in 0 makes it undefined. And if we look at this factor right here, 3x to the fourth plus 2, is this ever going to equal 0? Well, what happens if you plug in any number and raise it to the fourth power? It doesn't matter if it's positive or negative, it's always going to give you a positive output here. And if I'm adding something to that, I'm still going to get a positive. So this portion, this factor, will never equal 0. Therefore, this graph has no x-intercepts. It never crosses the x-axis. Notice that the numerator is only equal to 0 when x is 0, and that corresponds to a hole in the graph. Okay, that is not an x-intercept because the denominator is also 0 when you plug in 0. What about y-intercepts? Well, to find y-intercepts, you evaluate f of 0. We plug in 0 for x. Well, if we plug in 0 for x, we get 0 divided by 0. And notice that dividing by 0 is undefined, meaning that we do not have a y-intercept either. All right, interesting graph so far. No horizontal asymptote, no x-intercept, and no y-intercept. Let's plot the information that we have so far. We know that we have a vertical asymptote when x equals 1, so we can plot that vertical asymptote. We know that we have a hole in the graph at 0, comma, -2. So I'm going to find the ordered pair 0, -2, and I'm going to put an open circle on the graph. All right, there is 0, -2. Now we need to plot a few additional points. Well, in this particular case, I need to plot a point to the right of this vertical asymptote. So what's the easiest number to plug in? Well, we can plug in 2 into our function. 2 is probably the easiest number to plug in. And where do we want to plug it into? Well, we could plug it either into the original form or into the factored form. Plugging it into the factored form is actually a little bit easier because these 2's would cancel out. So we don't have to worry about these common factors. All right, if I plug in 2 for x, 3 times 2 to the 4th power plus 2, that gives me 50 divided by 2 minus 1. 2 minus 1, well, that gives me 1. And so 50 divided by 1 gives me 50. All right, I have the point 2, comma 50. 2, comma 50. That's going to be up here. So what does that mean for this portion of my graph? Well, as I go to the left of this point, I get closer to this vertical asymptote. And by definition, if I have a vertical asymptote, the graph either has to go down to negative infinity or the graph has to go up to positive infinity. In this case, the graph must go up to positive infinity. It cannot go down because that would require the graph to cross the x-axis. And if it crosses the x-axis, that would require me to have an x-intercept. But because there are no x-intercepts in the graph cannot cross the x-axis here, and therefore my only option is for it to go up as it approaches this vertical asymptote from the right. Now, as I move to the right of this point at 2, 50, all right, I have one option, okay? The graph can't go down because it can't cross the x-axis. It can't approach a horizontal asymptote anywhere because there is no horizontal asymptote. So if it's not going down and it's not approaching a single number, my only other option is for the graph to go up. All right, so this is what my graph would look like in this portion of the sketch. All right, let's consider what's happening down here. So I have this hole in the graph at 0, -2. Well, as I move to the right of this hole, and my graph has to be connected to the hole, by the way, that's important to recognize. As I move to the right of this hole, I approach a vertical asymptote. By definition of a vertical asymptote, the graph either has to go up or it has to go down as it approaches this vertical asymptote. Because I am already below the x-axis, the graph must go down to negative infinity as we approach this vertical asymptote. Right? It can't go up because that, again, would require it to cross the x-axis and require a x-intercept, which there isn't one. All right, so again, as I move to the right of this hole, the graph must go down to negative infinity. Now, as I move to the left of this hole, all right, my options. Can this graph go up? No, it can't. That would require it to cross through the x-axis. Is it going to approach a single numerical value or a horizontal asymptote? No, because I don't have a horizontal asymptote. So if it's not going to go up and it's not going to flatten out, my only other option is that this graph must go down as my x values go to negative infinity. All right, and so that's what the shape of our graph will look like in this portion of the sketch. All right, and so if you were to plot this in your calculator, here is what the actual sketch would look like. Now, again, are you going to know that this is going to drop down below this point here? All right, No, not necessarily, okay? All right, but should you be able to get the general shape from your graph? Yes, right? We know that the graph has to go up as x goes to positive infinity, and the graph has to go up as it approaches this vertical asymptote from the right. And we know that the graph has to go down to negative infinity as we approach this vertical asymptote from the left, and that the graph has to go down to the left as x goes to negative infinity. And there we have the sketch of our rational function, our third and final example.